Good morning, friends. Welcome to Water Resources Engineering class. So we have started the fourth unit. And what are the basic things of groundwater hydrology? Yesterday we have dealt all those things. So in today's class, we move into the following observations were made on a 300 mm diameter well penetrating an unconfined aquifer. Rate of pumping he has given, that means discharge is given. Drawdown in the test well 30 meters away. So that means there is one well which is 30 meters away. This is the drawdown in that. There is another well at 60 meters away from the main well. That drawdown is here. Depth of water well before pumping, that means initial water level is 50 meters. Determines the radius of the circle of influence and the coefficient of transmissibility of the aquifer. Remember that the only equation that which we have is only this. Any manipulation in the unconfined aquifer, you have to do only with this, no other alternative. So I took the same thing. So now I started thinking actually, what should I do? Right? So initial H, anyhow he has given 50. Okay? And then actually if I take it, for example H, it is at the well. So I don't know what is small h value. So what I have done here actually, Q is equal to 1.36 into K into H square minus H1 square or H2 square, anything you can put it. If I put it actually H2 square divided by log base 10 R by that radius, whatever it is there, that radius is how much actually, which is how much actually, 60 meters. This is the way. You can put instead of H2 here H1 square. By H1 square is how much actually, 30 meters. Anything you put it. Why I am doing all this? I want this R. Right? If suppose that fellow has given basically this H itself, well, at the well, what is the H he has given? Check it. At the test wells only he has given. At the original well he has not given. So we don't have any alternative except to go to the other thing. If he has given what is the drawdown at the well, then I should have used this R, small r, and then I should have used basically that H and calculated. So the moment it is not there, only this H and H represents actually the initial level where the drawdown is 0, and at any level actually where at the well I have taken where the drawdown is maximum. In the intermediate portion also you can see, because the drawdown curve always says that if suppose this is the impervious thing and it is your well actually which you are doing it, and this is the ground level, right? This is the initial water level, and this initial water level is slowly, this is how it decreases, right? This is how it decreases, right? And this is what we call it as cone of depression. So this H is not given. So otherwise I should have taken that only. So he has given one well is here and one more well is here. And this is what he has given, R1 and R2 he has given. And this drawdown he has given, this drawdown and this drawdown. I used one of them and did it. So by using this naturally everything is known. K is known to me, and K is also known or not known. K is what is the value of coefficient data. Coefficient that is also not known actually. That is also not known. K, here there are two unknowns. K is unknown, R is unknown. So what we have done is use the observation well data, right? I will write here, check it up. So first observation well, if I take it, first observation well, if I take it, right? What can I write? Q is equal to 1.36 into K into H square minus H1 square divided by log 10 R by R1. That is there. Similarly, second observation well, if you take it, second observation well, Q is equal to 1.36 into H square minus H2 square divided by log base 10 R by R2. So both the equations. Why? Because it's not one unknown. K is unknown, R is unknown. So with one equation, I cannot solve two variables. I need two equations. So that's why I have put. But Q is same. Right? So equating these two equations, that is what precisely I have drawn. So our problem is there are two variables. Two variables. Why two variables? One is K is unknown, and similarly the other one is capital R is unknown. So that's why what we have taken. What is happening at observation well 1? What is happening at observation well 2? Both are equated because discharge remains same. So when I equated both, naturally I can find out. Basically, first thing is what is R actually. So that's how we found out, basically solving these two equations. We found this. Then Q is equal to, I have put it, substituting Q and R, I should find out K also. Then coefficient of transmissibility is nothing but actually, generally this coefficient of transmissibility is only used in the case of confined aquifer, but somehow people use it everywhere. But coefficient of permeability is for unconfined aquifer, coefficient of transmissibility is for the confined aquifer. But he has given question is for an unconfined aquifer he wants transmissibility. The only way for calculating that is K into the entire thickness of the that means up to the water table, whatever is there, that which I should take it. K into capital H we can take it and then calculate it. So kindly remember how I have done from this, because if I see it here by equating these two, this K value will be eliminated. So only R is there. So find out R. Once R is found, then use the equation and find out what is K. So that's how once K is found, you can find out transmissibility. Another problem also we will look into it. A tube well fully penetrates an unconfined aquifer. Calculate the discharge from the tube well under the following conditions. Now, diameter of the well he has given, drawdown he has given. Drawdown means if he is not specifying anything, we take the drawdown is at the well. Effective length of the strainer under the above drawdown, that is thing. Effective length is nothing but actually this is L, which is called as small h. Then coefficient of permeability he has given actually, and radius at zero drawdown, that is nothing but radius of influence. But still any question whatever he gives, I always start from the fundamental equation. The fundamental equation for me is always this: 1.36 into K into H square minus H square divided by log base 10 R by R. So that is the only equation. But my question is, H is available? Anybody in the data? H is no. So H is not there. Only K is there. Okay. And small h is also there. R is there. Small r is there. Right. So what we have done in terms of drawdowns he has given. Again we started. That too, length of the strainer is also given. So the length of the strainer is nothing but small h, nothing to worry much into that. So we just manipulation, some small manipulation we have done here. Check it what I have done. H is equal to, S plus H. Because if you remember, this is the impervious portion. This is the well. This is the ground level, and this is the initial water table, and now pumping has started. Then naturally this will go down like this, and this also will go down like this. So this is S and this is H, right? And this one up to here, this is capital R. These are the basic things. So what I can do is, so this total is what we call it as H. So H is equal to S plus H. H square minus H square is equal to H plus H into H minus H. Therefore, I can write this S plus H here, S plus H minus H here. So it is S plus 2H and this is S. So H square minus H square I can replace by S into S plus 2H. That is what precisely I have done here. This is what I have done. Now this H is nothing but L. So I have made actually this 1.36 into K into basically S into S plus 2H. So I have taken divided by base into this 2 also I removed it. So if I remove it, naturally it becomes 2.72 S by 2 plus H. This is nothing but H. That's what first thing. Once I know it, now substitution only, directly you can substitute, K you can substitute, S you can substitute, L you can substitute, R you can substitute, small r also you can substitute, you can get that. This is also another equation you don't need to muck up actually, you can do any point of time. So what is the principle I have used? Q is equal to 2.ks into S by 2 plus L divided by log base 10. This doesn't change. This is what we call it as Q. This is another equation for solving any problem in the case of an unconfined aquifer. A tube well penetrates fully an unconfined aquifer. Calculate the discharge from the well under the following condition. Diameter of the well is given, drawdown is given, effective length of strainer is given, coefficient of permeability is given, radius at 0 drawdown. Same, this can be modified like this. Just now I have done. If it's substituted, you can get the answer. Kindly check where is there any difficulty at any point in this problem actually. The straight we can write that this. The only thing is you should remember this, how I am writing it. Only thing is capital H is equal to S plus H. Then naturally based on that H plus H is equal to this, I can H square minus H square is equal to H plus H into H minus H. That is the only thing which you should remember. And how to calculate these type of calculations also you should be familiar. If you want to solve any problem in groundwater calculations, please check it out. Then there is another question actually here. A 0.4 meter diameter well penetrates an unconfined aquifer whose bottom is 80 meters below the undisturbed groundwater table. When pumped at a steady rate of 1.50 meter cube per minute, the drawdowns observed at 2 observation wells. He has given 2 observation wells and determine the drawdown in the well. So what finally he wants is drawdown in the well means what is S. This is the calculation which he wants. So data given is H is given, Q is given, then R1 is given, R2 is given, S1 is given, S2 is given. What is K, what is H, what is S? Because if you want to determine S, you should know H. And if you want to know H, you should know K. That is how the discussion completely. So what I have done, 1.36 into K into H square minus H square by log 10 base R by R. So instead of H square minus H square, I used the observation well data. H2 square minus H1 square divided by R2 by R1. That is also right. So then what is H2? What is H1? And I calculated the same thing actually, H2, H1, so that I can substitute here. The same thing, H2 square minus H1 square log R2 by R1 I used. Then I found K value. Once K value is determined, then I substituted in this one H1 I removed. Instead of H1 I put it as H, and instead of R1 I put it R. Because the equation anywhere it is only different wells, so that I put it. So then I substituted it. Then I got actually first thing is H I will get 69.82. So total minus 69.82 gives the S value. Please remember the figure 100 times I am drawing actually. So this is the impervious portion. This is the well actually, and this is the ground level. Then initial water table is this, right? This is what we call it as total H actually. The cone of depression, how it forms is like this, right? And this is what we call it as small h, and this is what we call it as drawdown. So that you should remember actually. And if you have observation wells, so for example here and here two observation wells, so this radial distance is r1, this radial distance is r2, and this is s1 and this is s2. So this completes to me one topic regarding this unconfined aquifers. So we started with Darcy's law, right? Once the Darcy's law is finished, we took up Dupit theory. What are the assumptions of Dupit theory? What are the limitations of Dupit theory? And then straight away unconfined aquifer you take it. Please note that in the unconfined aquifer, the initial water level is nothing but the water table. That is the first thing you should remember. From there, different notations, whatever you have done, and final equation is what actually? It is 1.36 K into H square minus H square divided by log capital R by small r. So instead of H square minus H square, you can use H2 square minus H1 square, but accordingly R by R is nothing but R2 by R1. So this you should remember, and the same equation can be written in terms of drawdown also, you can write it. So that completes to me one topic actually, which we call it as flow, the radial flow to a well in the case of an unconfined aquifer, how to find the discharge. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.